We'll start off with the very first lesson and discuss units of measure, such as current. So what's the unit of measure of current that we use? Amps. All right. And what is, how would you define current?
1 ampere is equal to 6.
Not literally defined, but just give me a generic definition, something very general. What is current?
Electrons.
Flow of electrons. Very good. And voltage. What's voltage? Difference of potential between 2 points, right? Okay. Very good. What's its symbol?
V.
V. Okay. What about charge? Coulomb. Okay. And that's electric charge, right? Charge that flows. All right. Resistance. What's resistance?
Opposition to current flow.
Opposition to current flow. Very good. What about conductance?
The ease of current flow.
Ease of current flow. Outstanding. What's its symbol? Conductance. G. No, it's G. Its unit of measure is Siemens. Okay. Very good. And power. What is the unit of measure for power? Watt. Very good. P for power is equal to I for current times E for voltage. Yes? And in this power formula, we stated that power is directly proportional to what? Current. Anything else? And voltage. Very good. We also learned that we can define voltage in terms of what? Current times resistance, right? Current times resistance. And in doing so, we also established a relationship there between voltage and current. What was that? Directly proportional. And what about voltage and resistance? Voltage and resistance?
Directly proportional.
Also directly proportional. Now, if we move some things around here, we could say that current, while remaining directly proportional to voltage, is in what proportion now to resistance? Inversely. Okay? Inversely. We also established a relationship between conductance and resistance. What was that? But how would we define the relationship? They're opposite, basically. They're indirectly proportional, right? So we said that conductance G is equal to 1 over resistance R, and vice versa. So they would be indirectly proportional. Any questions about that? Okay, so let's say we are given a unit of power equal to not power, but rather voltage equal to 3.5 volts. And conductance equal to 85.71 millisiemens. And we wanted to find out what the power was. How would we go about doing that? How would we solve for power?
I squared, or 1 over 85.
Okay, well let's take a look at our two formulas, and let's bear in mind the method that I went over when we covered this in the lesson. I said we need to consider a couple of things. Number one, what we're given. Number two, what we're looking for. Right? So what are we given? Well, if we examine these two formulas and we plug in what we're given, we will find that we're given E. That exists in both formulas, does it not? All right. So we're given an E. And we're given a G. And we're given a G, right? Now G does not exist in either formula as we know it. However, we know that G is equal to 1 over R, and therefore R is equal to 1 over G. And if R is equal to 1 over G, then we can represent G wherever we find R. Can we find R here anywhere? Yes. Okay. So we also have R. And no R right here. The last thing that we'll do is say, what is it we're looking for? Well, we said let's find power. What is power? Okay, so we will underline power, and then what variable does that leave unaccounted? I. So that tells us, using this method, that if we identify what we're provided and identify what we're looking for, then the variable that remains is the variable that we need to solve for. In this case, we need to solve for I, for at least one of the equations, and then substitute it into the other equation. So let's solve for it here. We find that I equals P over E, yes? Okay. So if I equals P over E, then I can take this and plug it in there where I see I. Okay, well I've got E, and I've got my I right there. So I'm going to plug in my P over E. Okay, now, in this formula here, do I have variables that represent what I'm provided and what I'm looking for, but leave nothing unaccounted for? Yes. I've got G, which is represented by R. I've got my E. There's an E and E. And I've got my P, which is what I'm looking for. We're looking for P, so let's put everything in terms of P. Well, I can take down these parentheses by multiplying the R through the numerator. Is that correct? Yes. I can then move this E over to the other side by what means? Cross multiply, right? That which would give me E, moved up here would be E times E, giving me E squared, and that's equal to PR. Now, how do I isolate the P from there? Divide both sides by R and multiply by its reciprocal. So I divide both sides by R. And I find that P is equal to P squared over R. And now at this point I can plug the numbers in and solve for P. Any questions there? Okay. What are the three temperature coefficients that we will do? Positive, negative, and zero. Very good. Okay, let's talk about positive temperature coefficients. How's that defined?
If the temperature goes up, the resistance goes up.
If the temperature goes up, the resistance goes up in metals, right? Basically in pure metals. What about a negative temperature coefficient?
Semiconductors, positive. Temperature goes up, the resistance goes down.
In semiconductors, correct. Temperature goes up, resistance goes down, and vice versa, yes? All right, good. And lastly, zero temperature coefficient. What do we know about that? Temperature has no effect on resistance. Found in some crystals and alloys. Very good.